without age must go away, and then this age must go away. And this is the sequence, not the other way around. All terms without age must go away, and then this has to disappear. And then I apply the limit. Please do not drop the limit operator. If I write this, it makes no sense. This limit does not equal this. No, it does not. It equals this limit. So now the numerator, 2x minus 2x will be 0, to h, -1 plus 1. And then h in the denominator is square root of 2x plus 2h minus 1 plus the square root of 2x minus 1. I'll simplify. Now the limit operator will be applied, and I can write the final answer. Can anyone give us the final answer here? Anyone?
2 over 2 times the square root of 2x minus 1.
Excellent. And of course, these two go away. So the final answer, let me not write it here, there's not enough room, is 1 over the square root of 2x minus 1. Perfect. That's it. What does this function do? What does it say? So let me write the function one more time here. The square root of 2x minus 1, and this is its derivative. Okay, so now my question is, can anyone give us the domain of this function? What do we have to write? This will not stay.
I think you set 2x minus 1 greater than or equal to 0.
Brilliant. I move 1 divided by 2. So the domain of function f is 1/2 to infinity. Now look carefully at this function also and say f of x is not differentiable at and y. Anyone? It's okay if you're wrong. What is the difference between these two functions? This one exists at the particular point, but this one will not. Which point is that? Or which x value is that?
1/2.
Exactly. So see, this function, when you graph it, it starts at 1/2 and looks like this. And here's the problem. At this point, the function 2x minus 1 is not differentiable. Why? It has a vertical tangent. So that's why the domain of f prime is this. So if you ask me what is the rate of change of this function at 1/2, I'll say sorry, there isn't one. If you ask me what is the rate of change of this function here, let's say for x equals 4, oh, I can. F prime of 4 is 4 times 2 is 8, 8 minus 1 is 7, so it's 1 over the square root of 7, which is the same with the slope of this line and the instantaneous rate of change at 4. But if you say find it at 1/2, I can't. I'll say sorry. I can plug in 1/2 in here. Good, enough of that. So now here are my topics that I want to go over. Of course, more limits. I want us to look at a graph of an A function you want in which we have a point P and a point Q, like from section 2.1. I want to look at, if we still need to, a piecewise defined function. I think we had enough, but I don't know if you want to. An epsilon delta, I think we had enough. I don't know if you want to go back to it. The squeeze theorem. IVT, I think we had enough, but it doesn't matter. I want us to look at an example of a function with vertical and horizontal asymptotes and identify those. And an example with what I call gibberish, example of a function, example of a graph of a function. So these are some notes. So let me just say, we can go back to limits of all types with the 3 indeterminate cases, infinite limits, and so on and so forth. Graphing a piecewise defined function, identify when it's continuous or not, or differentiable or not. The epsilon delta definition, the squeeze theorem to find a limit, the intermediate value theorem for continuous functions, a function with vertical and horizontal asymptotes, and the gibberish one that I like so much to call it gibberish, an example of a graph of a function given conditions. What would you like us to continue with? And this one with a point to determine and estimate the tangent here. Yes, I'm sorry, forgive me, sorry.
Limits.
Okay, so let's take a look at more limits. So that's a real wide topic. So let's identify what we want. We want limits as x approaches infinity. We want limits that give us positive or negative infinity, or maybe D and E. We want to look at, we already discussed rationalizing, so I think rationalizing is clear. We had 2 examples today with rationalizing. Simplifying, absolute values. Any particular one?
Limits as it approaches positive or negative infinity or D and E.
Okay. Oh, this one. Very good. So these limits are at the beginning of the chapter. So these limits are in 2.2. So let's take a look. The limit of a function. And they are, I'm going through the book quickly to see, they are 93. So 2.2, yeah. Okay, so now I'll let you choose. I'll indicate which ones, and you choose. So we've already graphed something like this. Okay. If you want to review something like this, we can from the end of the chapter this time. So, okay, so these are the limits. So from 29 to 40, so you choose. I'll go back.
36.
36. This one. Very good. Awesome. So let's start with 36. And we have limit as x approaches pi from the left of the limit of x cotangent x. Okay, so the limit as x approaches pi from the left from x cotangent x. Perfect. So the first thing we need to do is always what? What is the first thing we need to do? When we're asked to find the limit, the first thing I need to do what? Anyone? Always.
Plug it in.
Plug it in. Very good. So assuming it will allow me to write on top of it, let me use something else. Okay, this was cotangent x. Good. So there is no problem here. Who cares? When x approaches pi, this approaches pi. So there was no problem with that x. So now let's see what this is. And I remember that cotangent x is cosine x over sine x. Next thing is I have to picture the unit circle. And I know where pi is. Here's pi. Pi from the left means here, with angles smaller than pi. Not more than pi, with angles smaller than pi. Where I know cosine is negative and sine is positive in the second quadrant. Now, at pi, the problem is that sine approaches how much?
1.
Careful, that's for cosine. So remember, on this axis, yes, cosine. On this axis, sine. So that's why at this point, because it's on the x-axis, the x value is 0. So this approaches 0 and this approaches 1. And we know that this is no hope. It's guaranteed, right? This is a number, who cares? You can even forget about it. But this is a number that is not 0 over 0. So I know it's no hope. No hope means this, this, or this. It's from one side. This is possible, but unlikely in this case. But it's possible. Okay, so then let's see. The numerator is positive. The denominator, the numerator is negative. I meant to write, of course, negative 1. So the numerator is negative and the denominator is positive. And who cares about this number? Nobody. So then what will be the answer that has to be written right away?
DNA.
Negative infinity, right?
Infinity.
The numerator is negative, the denominator is positive, so I have to write negative infinity. So this is possible, but unlikely. Why? Because the limit is from the left. Can I still get something like this? Yes. Let me share my screen. So it is possible, even from one side, for the limit to be DNE. And we had an example, here it is. So here the limit is oscillating. So from the left-hand side of 5, it's DNE. But these are specific situations. If it's from one side, it's normally infinity or negative infinity, one or the other. But if it's from either side, it could be DNE. But this is a very, very specific situation in which from this side is DNE, from this side exists. Okay, good. Okay, I didn't mean to stop sharing. I'm sorry. I meant to go back down. Is there anything else you would like to see here from 29 through 39? And yes, I can never forget this. when x approaches a number and I get infinity or negative infinity, I have to write that x equals pi, a vertical asymptote. Okay? Okay, so I'm sharing my screen again. Would we like to choose something else or we move on?